Hello, I'm Steve Vardaman. This is the fourth and last of this series of short introduction videos to this material on modern multivariate statistical learning. Uh, in this video, I'm going to do the last part of this Module 2 and in particular talk mostly about cross-validation as being a means of choosing a good level of complexity for a predictor in a supervised learning problem. So here is where we'll take off in this discussion. We've discussed the fact that one has to trade off variance against bias. One has to trade off model error against fitting error and so on in trying to find a good prediction methodology. So how more or less technically can one go about doing that? Well, maybe the most obvious thing to try would be to invent a empirical version of this ERR quantity, that is this generalization error. The most obvious way to try to do that is to take observed training Y's and for a predictor F hat built on the training set, plug in corresponding X's, compute losses, and then average across the training set to get not a cap ERR but a what I'll call a lowercase ERR. This is the so-called training error for a prediction methodology. Now, the biggest problem with using this method of quantifying what a predictor is likely to do is that it just doesn't work. The problem is this, that typically as a function of complexity, ERR, little ERR bar, will simply decrease with increased complexity. So if I had a set of axes here and the complexity goes this way and ERR bar goes this way, then ERR bar as a function of complexity just does something like that. The problem is that if I also plotted cap ERR, the actual not training error, but test error as a function of complexity, it doesn't do that. Rather, it typically does something like this. That is, it increases after a certain point. That is, you can decrease cap ERR with increased complexity up to a point, but thereafter increased complexity just degrades ERR. So we need to do something other than just use the training error to choose among prediction methodologies. What one might try to do is to employ other measures besides ERR bar. So there are things like MalloCP, AIC, BIC, things like adjusted R squared and so on that one might try to use to predict predictor performance. Another possibility is in very large N context to basically hold back some random sample of the training cases to serve as a test set. fit on the bulk of the data to produce f hat, and then use the test set average. So this is over cases in the test set. That's where the y's are coming from and the x's are coming from, but the f hat is coming from the training, the part of the set that was used for training. That's a possibility, but it's not all that common to be in possession of so much data that this makes people happy, or this makes good sense. So instead, what one might do is to use sample reuse methods. I'm going to talk here about cross-validation, and later we'll have some things to say about how the bootstrap idea might be used to estimate ERR, but for right now we'll talk about the most common methodology, probably the most effective methodology, and that's the idea of cross-validation. So here's what cross-validation is about. What one does is to break a training set into K pieces. So we'll call them T1, T2 up to T cap K, roughly equal size. If cap n is divisible by K, then we can make them actually equal sized. Just do the breaking up in a random fashion, and then train on the training set minus each one of the folds, the smaller pieces of the training set, to produce cap K predictors, f hat super little k. So I'll have a T1 that gets left out to make f hat 1, T2 that'll get left out to make f hat 2, and so on. Then I say to myself, well, I didn't use TK in order to make f hat k, so what I might do is see how well I do at predicting the points in TK using f hat k, and in fact do that for TK, T1, T2 up to T big K, and in fact average for each training point. I will find the fold that it is in. I will find the corresponding predictor with that fold eliminated, or fit with that fold eliminated. I'll plug in the X and the Y, I'll compute a loss, I'll add up across all of the training points, and that will become, I'll then average to get a so-called cross-validation error for the method. One hopes that this cross-validation error for f hat then approximates ERR, and that ERR is a plausible, or is a good indicator of how well a prediction method can be expected to do. A question that has to be answered here is, how does one choose the number of folds for cross-validation? If I make a fold for each data point, that is, I leave out data point number 1, fit, leave out data point number 2, fit, leave out training data point number 3, fit, and so on. Sometimes it turns out that it's possible to compute this cross-validation error in a very slick way, and actually it's not an impossible calculation. That makes one think that, well, maybe the best way to do this is to try to do leave one out cross-validation. And because after all, cross-validation actually estimates ERR for a training set of not size n, but size n times 1 minus 1 over big K. And if big K is not small, there's a difference between the ERR that's actually being estimated and the ERR that I'd really like to have my hands on. On the other hand, leave one out cross-validation tends to produce large variance in terms of estimation of ERR. And the reason is that the F-hat Ks are built on nearly the same training sets. As little k goes from 1 to big N, they produce similar results. And so the averaging that you're really counting on, to reduce variance when you compute the cross-validation error, you don't get it because of the positive correlation between the things that you're averaging. And so consideration of bias variance trade-off makes it very common to do cross-validation based on k-folds of k equal 5 or k equal 10. A common method then of choosing between levels of complexity is to do k-fold cross-validation, find the complexity producing the smallest realized cross-validation error. So I might have, for a very simple-minded example, I might be doing polynomial regression of orders 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I look for the one that has the smallest cross-validation error, and then compute a standard error for that prediction error. Now, what does that mean? That means that for each fold, I compute a test error for the fitting with that fold left out, and make a standard deviation of those. Okay, so that's a sample standard deviation of these test errors. And then the standard error that I'm talking about would be that standard deviation divided by the square root of k. So the idea is I find the best cross-validation error, but I then move back towards a more I move back towards less complexity as far as I can. And as far as I can, a reasonable rule of thumb, a popular rule of thumb is this. I move back towards smaller complexity until my cross-validation error is larger than one standard error above the minimum cross-validation error. And that the idea there is that rather than have a predictor that's too complex and overfits, I'll try to push in the direction of having a simpler predictor.